So friends, welcome to this course, Thermodynamics of Materials. So Thermodynamics of materials. So previously course name. Previously this used to be called metallurgical thermodynamics. When I was a student, I used to call it metallurgical thermodynamics, in short made thermo. Worldwide, this name. But with the advent of materials and importance of materials, they have changed the name, and it has been called now thermodynamics of materials. And most of the times, since we are metallurgical engineering, so we consider mostly metallurgical engineering systems. Now I get into the discussion, opening discussion with the introductory terminologies of this subject. So that means I am going to take up the introduction with the view to introduce you with the terminologies. And this is very important if you want to master this subject. So this your comment of these terminologies, your concept about this terminology is very important. Otherwise you will not be able to actually have full comment, or you will not be comfortable with this subject. You will be very shaky. You try to avoid this, evade this subject. If you don't have a comment of this, and subsequently also, once you are equipped with this, then you will, of course, you have to continue in the same way, same vein. Acquiring the knowledge of the subsequent chapters also. So each class will be equally important, but since it is introduction, so introduction is very important. Now I start. What are the introductory terminologies? I start. First is, I will go by 1, 2, 3, 4, etc. Very systematic subject. Like mathematics. So first is system surrounding and universe. Surroundings and universe. These three we will actually take up. Now I tell you one thing. Maybe you have come across this terminology beforehand in some physics subjects, chemistry. But I suggest that you follow what I am saying now. Even you may forget. I don't mind, and you see no problem. No harm. You forget previous classes, but you follow or previous discussion. So you follow my class, and you will often see that I am talking something new, even with the so well-known terminologies, well-known topics. For example, start. System. What is system? System is the part of the universe, chosen for study. System. And then surroundings is the remaining part of the universe. The remaining part of the universe. The remaining part of the universe. From which we may conclude system plus surrounding will constitute the universe. Surroundings together will make up universe. A good application for this is, I tell you, consider any one property, thermodynamic property, post property. Thermodynamic properties will come across. Just take one, say internal energy. So what do you say? So, for example, you see, E is the internal energy. I use this often. Internal energy. So, how we use this? Apply this internal energy of system plus internal energy of surroundings is internal energy of universe. Now, I'll tell you one thing here at this stage. So, is this? What's that? So, many authors these days, many people don't use this surrounding universe. This one, system surrounding universe, and this second law or first law of thermodynamics are stated in terms of universe because this is based on the idea that there is nothing outside universe. But after the introduction, after the discovery, after this second law, what is this called? I'm sorry, theory of relativity by Albert Einstein, where it was shown that universe is expanding universe. So thereafter some authors or students, they are reluctant to use universe. And together constituting was the universe itself is expanding. Normally it is considered there is nothing outside universe. System, surrounding and total within universe. But this is actually they are reluctant. But I have seen, I can tell you, even it is expanding, still it is universe. I give counter argument. Even it is expanding, it is universe, within universe, nothing outside. So moreover, you see, if you use this concept, this will make this study very simple. Simple and it will easily follow. Because we often use surroundings, system, together universe. Now then what they do? Suppose they don't use the word universe, what they do? They say isolated system. They use the term isolated system. Universe is an example of isolated system. I will take up soon, but this actually gives you more. This will give you actually more insight, I would say, into the system and help you apply the situation, solve the thermodynamic problem more easily, apply the first law, the second law more easily. So I will have to stick to this conventional law, classical approach. System, surrounding, universe. You can cope with anything. Any other concept, any other convention, letter, convention, you can use. Isolated system, no problem. Absolutely no problem. So I will go by this. I want to separate system from something. Systems from surroundings. Remaining part of the universe. Start. So this is the beginning. Now take up the next one. Important is types of system. Now concept. Then you will note here, I forgot it. System and surroundings are separated. Surroundings are separated by a boundary. System, this is system room, and this is actually this corridor, maybe the part of surroundings. Then this is separated by the wall. So this is the boundary. Okay, so system and surroundings are separated by a boundary. So this is the first one. Second one is types of system. Type of system. Sometimes I write in short. System. Okay. So save time. Okay. See, what are the types? One is isolated system. Next is second is what? Closed system. Third is what? Open system. Now I start with isolated system. I will remove this because is isolated? Some start. First is isolated. Isolated system. There is no exchange of mass between system and surrounding. Between system and surrounding. Neither there is exchange of heat and work interaction. Neither there is exchange of, I should write exchange of heat and work interaction. Work interaction between. You don't have to exchange. Please do this. There is heat and work interaction. Just remove this. There is heat and work interaction between. I am writing here between system and surrounding. Very important. Isolated. No interaction with surrounding. No heat, no work, no mass. This is. Then I will give an example. Very easy example. Say one is they say this is actually well insulated practical examples. Examples. I will give example. Well insulated thermoplast. Thermoplast. You bring tea, any kind of beverage, you preserve thermoplast so that temperature remains there. It remains hot. If it is hot, it should remain hot. Cold. Temperature should be maintained. So no heat should dissipate from the thermoplast to outside because this is actually insulated. So well insulated, fully insulated thermoplast. So that there is no heat, there is no question of any work interaction. Work is expansion against the external pressure. There is no expansion, no chance. No heat, no work, and the liquid will remain intact. Amount of will not evaporate away. So no mass is lost into the outside. Surroundings. So this is actually one example. Thermoplast. Second is Second is again well insulated. I am not same time. Well insulated bomb calorimeter. Bomb calorimeter. If you ask me, sir, what is bomb calorimeter, sir? In calorimeter, it will do calorimetric work, and it determines actually the heat capacity of such things. So what is the figure like? So I am giving you. This is bomb calorimeter. You ask me, this is bomb calorimeter will use. So well insulated, and I am carrying out a reaction into this bomb calorimeter. See, close. Rigid, it don't expand. Totally impervious, and then I am carrying out a reaction. Very important reaction, sir. Metal solid plus oxygen gas goes to metal oxide solid. This reaction, this is like exothermic reaction. Heat will be released, but it will be remain inside. It will come out. Make sure. No way. Remain there. There is some reason. There will be some actually effect for this. Okay, the consequence for this. So what is this? Temperature, affect the temperature. These are discussed, but this is the bomb calorimeter. In fact, we will consider one example later on. See, universe itself. Suppose you consider the universe is actually encompasses everything, systems surrounding you. Then, what it will exchange with? It is actually sum total. There is two universe, and this universe will exchange with the second universe. So, universe itself. The So that's why I told you, they sometimes replace inverse by isolated system, but you consider this. That inverse is just an example, these three examples. So then what I am trying to tell you, the system is a system. What is a system? And this is the system. This reaction is a system. This is a reaction system. The liquid tea, hot tea is the system. What other things are boundaries. And outside is surrounding, no insulated, separated, no interaction. This case is a closed system case, no interaction. But surrounding is all the same there. On lookup, no interaction. Here also, it will be produced, it will come out, no interaction with the surrounding outside. Outside is surrounding. The whole thing, whole part, the remaining part of the universe, all surrounding. But when surroundings take part, it's actually the immediate part takes part. But there is no scope here also. This is perfectly insulated. This is okay. Then I tell you what it is called. This is later on. Later on I will explain, not today, it will time understanding. Later on you will see, later on, an isolated system is a constant internal energy, constant volume system. Make no mistake. This is actually a very mathematical formulation. Instead of these languages, it may be very smartly defined as constant internal energy. I am right. Yeah? So for this constant volume V system. When V for volume. V volume. This can be established with the help of the first law of thermodynamics. With the help of the first law of thermodynamics, later also. I don't want to take it up. See, this is so important. This is so important. Science was sitting back there. Other day he telephoned me and actually just you are reminiscing about this class. I said, still he says, I still remember that an isolated system is a constant internal energy, constant volume system. So important. He has actually followed this to the end and knows how important is this. But this is mathematical. Try to be mathematical, I tell you. Scientific, so very good. This I will explain. Why, sir? Sir, you said, and you believe. No, please do not. Do not do that. Don't have to believe. So I will tell you with the help of the, can be established with the help of later on. That's it. After the first one. The first one, I will establish. I have to. Well, what next is what we have considered? Yeah, you know very well what is the next is closed system. Closed system. Now with this, you will easily follow system surrounding interaction. Now follow. There is interaction between Now what is closed system? I just say in the system I will write short. There is interaction, heat and work, heat and or work. For the time being I tell you, it is a heating understand. High temperature, low temperature, it is fast. Work, for the time being expansion or compression. Volume change, good enough. Work. It's a mechanical work both. There are other types of work, non-mechanical work, like electrochemical work, surface of later on. So don't worry. So heat and of work. Oh, by the way, can I will modify this later, not today. I am coming back to isolated system. I'll add something on this. This is popular. This is also popular. You will get this in Gaskell's book. I will give you reference later. But I want to add also another one, that is, and no non-mechanical work. This I will establish when I shall discuss the first law. So now get back. What I am talking about, closed system. That is heat and work interaction between system and surrounding. Heat and work exchange. That is possible now. But, however, there is no mass exchange, mass transfer across the boundary, mass exchange. Again, between this, between system and server. This is actually. Now, this I have to spend some time on this. Again, as I told you, this introductory terminology is a fairly long chapter. 7-8 classes. Introduction 7-8. So you be prepared with this. Now next is okay. As I am discussing. Okay. So example. Example is okay. What expansion of a gas. Taken in a cylinder, heated with frictionless piston. Frictionless is a term. Frictionless piston. So one example. Okay, I elaborate this. I am taking this. This is the cylinder. This is the piston. There is a load upon it. Okay, got this. Okay, this is this, and there is a thermostat. Follow this. Follow. There is a thermostat. Thermostat means which will maintain temperature constant. This is such a process I am considering. Just for example, it's an isothermal process. What is in the system? Here, N moles, some amount, N moles of, we actually consider ideal gas, but introduction as well as for simplicity, ideal gas. This is the, follow me. What is the name of this? Tell me. This is thermostat. Big, huge thermostat. So that when heat comes into this, temperature is changed and it changes. Or it is taken away from this and imparted to the system, taken no change in temperature. So huge. You change in the set 10 decimal. You want to have actual experimental level. So thermostat. Or maybe it doesn't change at all. Thermostat is actually no mixture. I will tell you, ice water mixture. There is some thermostat. This is actually, and there is a load here. I tell you, follow this. There is a load. The load means weight. Weight means force. Force for unit area into pressure. This leads to a pressure. Say P1. And here inside pressure is what? Inside pressure P1. So system is in equilibrium, perfect. Means they are happy, very happy. No process will occur. Which system will carry out process? Thermodynamic processes, metallurgical processes. Process will, this is a very beginning. Must understand system, then carry out process with system. Concerning the interaction, surrounding. Okay, good point. So what is this? N moles. Let me write here P1. So P I could have written, but since I have thermostat, I have to write P1 for some. You understand? P1, how many moles? N moles. Say 1 mole. Ideal gas, say argon gas. No problem. So this is the one. And this is load. Load is external. And this is giving. Okay. What is the system? System is N moles of ideal gas. 1 mole of argon gas. This is the system. Then what are these? What are these? They all unknown. What is this? This is thermostat. Is a part of surrounding. And this is the load which is working on this system gas, compressing say or against which this gas is expanding. This is also part of the surrounding. This is the surrounding, this is the surrounding. Two aspects of surrounding. This side gas. So surrounding. This is also a surrounding. So you get this everything that surrounding, one surrounding. Why in which respect is important? Here heat will be transferred. Now why transfer? That's different issue. So heat exchange very possible across the boundary between system and surrounding. So heat interaction. I told you heat interaction. General heat interaction between system and surrounding. So this is heat interaction part. This takes care of heat interaction. And the other one gets, this is also surrounding. This takes care of work interaction. Because the load will be lifted means work is done. Okay? When it is expanded, say for example, then this load will be lifted means surroundings is lifted. So work against the surrounding. So surrounding, this is about work interaction. It may be compression. It may not be expansion. Compression then what will happen? Surrounding will work on the system. Who is it? And heat will be rejected from the system into the surrounding thermostat. Very good example if you ask me, I may forget. Good example of thermostat, you know, this atmosphere. So easy. So easily available, you see everywhere. Every moment. Earth atmosphere. Why? Huge. How many furnaces and industries are running? Furnaces, industries like machines, cars, and heat is released. Okay, you are concerned about this. Okay, carbon dioxide emission. But heat is coming out. Has it changed? Oh, this factory is running, that's why temperature has changed. Atmosphere temperature, it is still remaining today maybe 27 degrees or 20, 30. It's winter, it will be 16 degrees, 17 degrees. Who will change? Huge. Who will change? Who can change an infinite one? Say, up infinite. Who will change? Any amount of heat, infinite will change, reach to zero. Zero change. Okay? It is perfect infinite. So another example is third example. That's about thermostat. What is the example of thermostat? Earth's atmosphere. Like this, important things. This is thermostat. This maintains temperature. Another thermostat is, I tell you, this is the electrical furnace. There is actually no temperature controller, which works with the help of relay. Controller with the relay. Control temperature. So anytime there is tendency of temperature rise, this circuit is cut off. And temperature remains there. And anytime there is a tendency to decrease the temperature, furnace turns on and maintains the temperature. We say temperature controller. Temperature controller is the thermostat. This is actually thermostat. I should mention example of thermostat. Examples of thermostat, which is part of surrounding. The thermostat is what? Good thermostat, I should say, wants a art atmosphere, huge art atmosphere. Okay. Second is what? I would say control, temperature control in a electrical. Okay, temperature controller. In electric furnace. Okay, furnace. Third is what? Third example, as I told you, what type? This ice water mixture, you know, what temperature it maintains? 0 degree. Okay, and anytime heat comes, ice will be made. Absorb the temperature and remains the same, 0 degree. And anytime heat is extracted, some water will convert into ice, releasing heat. Maintaining the temperature. So other mixtures are there, freezing mixture. Ice, sodium chloride, there are freezing mixtures. So freezing mixtures, etc. Freezing mixtures. Thermostat. These are the thermostat, but I am talking of examples here. One example, that is a post system. Coming back to post system. This is it. Now I tell you how actually this whole thing involves. Work done, heat, follow quickly. Just one example. So P1 equals to P1 here. Insert the P1, insert the P1. Same equilibrium is here. Now how will get a process? I want expansion. No expansion. We are happy. P1. Thermostat temperature what? Temperature what? T sir. This is the isothermal process and constantly. for example. Okay, and this is also what is the temperature? T. So T, no response. Say it will be happy, peaceful coexistence. What is the pressure? Pressure P1. But this is giving load downwards, this is giving upward. So process, now follow this, then you will understand what does it mean, expansion of the gas. Unless you destabilize this equality, upset this equality, nothing will happen. Upset. How the upset? Just I will not explain in this more. That I said, decrease this load. This load is reduced. This is a 10 kg, make it 9 kg load. So P1 minus delta. Or say, typically say, it is called say P2. Change P1 to P2. Say 5 atmosphere, 3 atmosphere. 1 atmosphere make it 0.5 atmosphere. So change the load. So as a result, what will happen? Upset P1 and that is P2. So it will expand, move up until, and when it expands, it will be P2. P2 after time. Then they again say this time. But in the process, what happens? Follow. See what is the ramification, consequence. Expand, work is done. Work interaction, come to picture. So what? Who is doing what? System is expanding, lifting the load which is surrounding. So working on the surrounding. System is doing work on the surrounding. So work done. So it is generally what heat interaction. You will other way for compression, but follow this way. Okay? Expand. So work interaction over heat. See, in this, to understand that there is heat interaction, you have to understand this way. Since thermostat is provided, its job is to maintain the temperature of the system. T, let T, at T, maintain. How you do this? The moment it is expanded, now suppose the heat is not supplied, this is considered. That's the way. I don't want to get into this complication. This is the adiabatic concept. That no heat is given. But suppose for the time you will consider no heat is given to you. Suppose thermostat is missing. Role of thermostat I will explain. Then what will happen? It is doing some work, and the first of thermodynamics which I will not state today, it will be done at the expense. Work is done by the system at the expense of its own resources. What is its own resources? Internal to the gas. So the moment it is at the expense of its internal energy, it is at the expense of temperature. Internal energy and temperature hand in hand. So temperature is down, but since now consider thermostat is there, all aligned, it will not allow changing temperature. So what it will do? It will provide heat, compensate for. No, don't change internal. No, I will give you the heat. Because this is a process where internal does not change. I will explain. There are many processes coming, at least 3-4 processes. I will explain that. But this process, so temperature, since it is isothermal process. If you ask me, this is isothermal expansion. But, example. So what? So don't let it just I touched upon house. What is heat interaction? Work interaction? Expansion of gas. So gas. Okay, happen. Okay. So go on. Next is what? Oh. So heat interaction you have understood. Heat interaction, work interaction. But you know that. What is the other criteria? Tell me. Is closed system what is the other criteria? To be a closed system, what is the other criteria? Tell me. You know it. Yes, there may be heat interaction, there may be work interaction, maybe both. But another.
There should be no mass.
No mass. Mass has not escaped. Also by there. They will expand it. Still very good. Nothing has escaped into the surrounding. So satisfied. Closed system. Now not only this expansion, we are metallurgists, we want to consider reaction. Again I show you this system. Draw this system. Okay, I'm drawing for you. I'm drawing for you. Again I draw. I take the pen. Again same picture. Second example. For expansion. Second example is what? First example. Second example. Tell me what is what? Yes. Carrying out a chemical reaction. Carrying out absorb, carrying out a chemical reaction in the previous system, carrying out a chemical reaction in a cylinder heat engine piston. Why I am taking this? I tell you why I am taking this. Acha, by the way, frictionless, why? Suddenly you say, frictionless, I want to touch upon this. In many books, you will not see this is addressed. Friction. But I tell you, why friction? See, normally what happens when expanded, heat is entering. When rejected, heat is rejected. When expanding, heat is supplied from surrounding to system. When compression, heat is rejected from system to the surrounding. Opposite. Friction is actually in reverse, means one-way track. So when it is expanding, the friction, it is generated. When coming back, compression, it is generated. It is not, it is actually absorbed. So that is one thing that complicates. Still another thing I will say. This frictional ring will interfere with the heat interaction. Makes it complicated. So that's why simplify friction layers. Avoid those unnecessary complications. Okay? Idealize it, no problem. Try to understand the ideal, then gradually complicate it and take up real systems. First consider an ideal system. Okay? So this is Hamilton, this is bottom back system. So how will you scale this? Similar yes? Etc. Understand? What is the system now? Not n moles of ideal gas. What is this? A reaction. Metal plus oxygen goes to metal. This is correct. In a closed system, in a closed system, previously it was isolated system. This can be a closed system, this is considered. There is actually equivalent to this. Later on I will take in the open system, but metal plus oxygen, metal oxide. Okay. So this is 2 over. Third is what I wanted to see. Third example is what? Closed system. Oh, closed system. Third example is very interesting. Badly insulated thermoplast. Badly insulated. Well insulated thermoplast. Isolated. Badly insulated. Why sir? Bad insulated, what will happen? Bad heat will come out. Heat interaction. Okay? Outside. Okay, very good. May not be work, but any of them will do. Very good. Fourth example is I tell you art itself. Art itself is a closed system. Previously contrast, universal isolated system. But art is a closed system because there is interaction between art and extra case, outer space. I will begin and do examples so you are totally I hope you are convinced or you have understood. Next is what can be open system. Open system. Third, remove this. Open system. And let me write this is very easy. Open system is what? You can guess. Now you can guess what is open. All possible. So exchange of time. Exchange of mass. Exchange of mass between system and surrounding allowed. And what second is what third? Heat and what heat and or what interaction allowed. Very good. Yeah, concentrate. Full concentration. I am teaching with full concentration. You will follow full consciousness. I have come here to teach you, not to cut jokes. What I said? What I said? I have come here to teach you, so that you know, you comment this subject as much as I do. You do not know, but not to cut jokes. Okay? Not to take classes, not to do attendance. Yeah. Propulsion studies are exchange of mass system allowed, and you can go on interaction also. Very easy, very easy. You are heating hydrogen. Example. Okay. What? Heating actually water in a bigger water stove. Heating water. Heating water in a beaker above a stove. Over the stove. You can very easily understand this. Suppose this is your beaker. You are taking some water, and there is a burner. What will happen? Water will. So vapors is actually shared with the surrounding, and heat from outside. This is surrounding. This water is only the heat is given. It interaction allowed and mass exchange allowed. This is example. Another is also this maybe not bad to get in here. He is what? Flow reactor. Example, flow reactor. This is a reactor furnace. Reactor is a furnace. Furnace has a temperature controller, heating element, insulation. The furnace is a furnace. Maintaining temperature T, and you are passing this gas, stream of gas. What is this gas? CO2 gas. Into continuously feeding, and so mass exchange, and is leaving. What is leaving? Yeah, the reaction is what? CO2 goes to CO plus dissociation reaction. Important one. This is what you get at the excitant O2 plus unreacted CO2. So what I try to tell you, mass exchange from the other side, heat is moving away because this is exothermic reaction. This is, I am very sorry, this is a exothermic reaction. So temperature will tend to go down. Furnace is there, ready there to maintain the temperature. So heat will be passed on to this so that temperature is passed. So first part, second segment is over. So next actually I will consider third. And let me write at this. So third introductory terminology 1 to over. Third is this way. I am writing 1 to this way. What? Arabic. Third one is what? This called yes, state function. And path functions. State functions and path functions. Let me check if I have any time left for today. I will check with you. Can I take 10 minutes? So let us close. Let us call it a day. Today we have to wind up. So thank you very much. Okay.